Okay, take your attendance first. Okay, key in your attendance. Okay, class. So we do question about ideal gas today. So yeah. So just be done with the introduction of the entire topic of ideal gas, right? Yesterday. So let's recall back. What's something new you learned about ideal gas? Okay. Okay. So what are the equations you learned first? Okay, yeah, of course. You heard about PV over T is found to be constant. Okay, then PV was nRT and PV was nKT. How this converted to this? The n changed to n over Na, right? Number of particles over Avogadro constant. Then R over Na was converted to K, Boltzmann constant. Okay, then a new discovery was done by using the kinetic theory of gas. They found that PV is equals to 1/3 Nm C squared. Okay, new formula discovered from kinetic theory, and the highlight is this speed. Okay, that speed call is what? Call it mean square speed. It's called mean square speed. Okay, just introduced last class, right? Okay, then after that, after discovery of these two formulas, these two was compared, and they found the kinetic energy of what? One particle is what? 3 over 2 kT. Okay, so this is the conclusion of this topic. Okay, so remember, the kinetic energy is directly proportional to what? Proportional to the temperature, absolute temperature or thermodynamic temperature. And the kinetic energy found to be directly proportional to mean square speed. We call it mean square speed. Okay, so this is the summary you have to really need to remember in your mind. Kinetic energy of the particle, one particle is just dependent to the thermodynamic temperature, and the kinetic energy is directly proportional to a new type of speed called mean square speed. mean square speed. Okay, then of course the temperature have to be in Kelvin for all the formulas. Okay, the K is a constant, and yeah, you have to use SI units for all the equation except PV over T, P1 V1 over T1 equals to P2 V2 over T2. The pressure and volume you can use any unit you like. Okay, but temperature have to be in Kelvin. Okay. Okay, so based on these equations, okay, let's try some questions. So of course today's lesson is about the mole concept. So if you drag down towards the end, yeah, so you have questions, assignment. Okay. So I hope you have the list of formulas with you. Okay. Let's try first question. Okay. So use the formulas. I just write the formulas again here. Easier. P1 V1 over T1 equals to P2 V2 over T2. First equation. PV equals to nRT. Second equation. PV equals to nKT. Third equation. Then PV equals to 1/3 nmc squared. Fourth equation. And the kinetic energy is 3 over 2 kT. Okay, 5 dominant equations, right? Okay, look at the first equation. What equation? How do you find the answer? 1 minute for you. Try to get the working. I know you focus in AS in your at home, but class, I try to recall back the idea, understand the concept. Later you need it for A2. The mass of a nitrogen molecule is given. This is the mass of a nitrogen molecule. The Boltzmann constant is 1.38 times 10 to the power negative 23. Calculate the root mean square speed of the nitrogen molecule at 17 degrees Celsius. Okay, this is root mean square. Root mean square. Okay, how to get root mean square? I really never tell you anything about root mean square. I skipped it, right, last class. Just mean square speed. Just root the mean square speed. That's root mean square. Okay. Let's say your mean square speed. Let's say your mean square speed is 50. Then this is your mean square speed. Just root it. Root mean square. This is a root mean square. Just root the 50. This is your root mean square. Root the mean square speed. Okay, it's called root mean square. Root mean square speed can say like an average speed of the particle. Average speed of the particle. Okay. Okay, please. You get 506 meter per second. Get the working. You can discuss with your friends if you want. Maintain SOP. Okay. Which formula is the best to be used? Calculate the root mean square speed for the nitrogen molecule at 17 degrees Celsius. So which formula do you think useful? You need to find the root mean square. You need to find the kinetic energy first, right? You need to get the kinetic energy first, right? So which formula? Number 5, right? Those who have thought about 5 is good. So you have to work out 5, right? Equation 5 to be used. Equation 5, right? Find the kinetic energy of the particle first. And that kinetic energy equate with what? Half mc squared. Then you find the mean square speed. Root it, you get root mean square speed. You want to work out? Get the working. 3 over 2 kT. Find the kinetic energy first. 3 over 2 K is 1.38 times 10 to the power negative 23. Temperature, change to Kelvin. 17 degrees Celsius, you have to change to Kelvin. How do you change to Kelvin? Plus 273.15. Don't just go 273. A levels, 273.15. Yeah. 17 plus 273.15 is the temperature. first question. Yeah, correct. Yeah. So yeah, 3/2 kT, right, to be used should be equals to half mc squared. So 3/2 k is what? 1.38 times 10 power of negative 23. Temperature is 17 plus what? 273.15 equals to half mass of the particle, right? Mass of the particle is how much? 4.7 times 10 power of negative 26 mean square speed. So find the mean square speed. Then you root that value. You should get the answer. This is meter per second. Mean square speed is meter squared as negative 2. Right. Okay, take down the working. I hope you have this idea earlier. To KT is half mc squared. So to get 506 meter per second. You only got 506. Very different 506. Okay, so this easy question. The question get tougher when go down. Okay, what we are doing, we want to try to familiarize with which is the best formulas, how the formulas can be used. Okay, so we go to the next one. You can now go for 2. Go to the second one. Okay, get me the answer, second one. Another 2 minutes. Finish this assignment today together. Use the following data to calculate the mean kinetic energy of the molecule of ideal monoatomic gas at a temperature of 27 degrees Celsius. Select the correct formula. What is the kinetic energy for a monoatomic gas at 27 degrees Celsius? Kinetic energy. So 302 kT. Okay, this is a very famous question, equation. 302 kT. So kinetic energy of particle is 302 kT. So of course 2 is 302 kT. But K you can use 1.38 times 10 power negative 23. In exam K value is given. But or K can be obtained by RONA also, right? RONA also K. So any book, just substitute the K, just 1.38 times 10 power negative 23. Temperature change to 27 degrees Celsius to Kelvin, right? Okay, I think it's not typical. Okay, I want to add something here. The 302 kT is, if you go further studies, okay, those who are maybe going for engineering, doing mechanical engineering, doing thermodynamic, okay, want to know about gas behavior, okay. The 302 kT is only works for monoatomic gas, just mono. Diatomic it doesn't work. Diatomic the formula is slightly different, 5/2 kT. But A level syllabus, just 302 kT. So the question they must say it should be a monoatomic. But A levels, monoatomic or diatomic, they still use 302 kT. They don't want to get you confused first. Further studies just tell you 302 kT only for monoatomic. Diatomic will be a different 5/2 kT actually. Polyatomic, a more complex molecule, it changed to 7/2 if I'm not mistaken. That's why the question here is monoatomic. Okay. So real examination, your levels, A levels, just monoatomic. You take it, the particle has a monoatomic. That's it. Okay. Okay, I believe all of you got the answer for the second one. 6.2 times 6.24 times 10 power negative 21. Got slight different answer. So 2 also use 3 over 2 kT, right? Second one also use 3 over 2 kT to find the kinetic energy of the particle. Those done 2, go ahead with 3. 2 minutes. Okay, 2 is proving. The ideal gas equation can be written as PV equals to nRT. So that use this equation to prove that density such a gas is given by rho m times P over RT, okay, MP over RT, where m is the molar mass of the gas. Capital M is the molar mass of the gas. Molar mass of 1 mole, right? So from PV equals to nRT, can you get the rho density is MP over RT? Come on, look up.
I left something.
Managed to get the third one. Clear this. Okay, so get the equation PV equals to nRT. So you need to bring molar mass and density in the equation. You need to bring the molar mass, and then you have to substitute density. How you can convert to become molar mass? Which one? Of course, the number of mole, right? The number of mole we can write the mass of the gas over the molar mass, capital M, right? RT. Yeah. So small m, the mass of the gas, divided by the capital M. Capital M is the molar mass. So can you bring density now? What combined can convert to density? What can combine to convert to density? Density is what? Density is mass over volume, right? Mass of the gas divided by the volume, right? That's your density. Yeah. So yeah, mass divided by volume, just combine the mass over volume, convert to density, right? PV equals energy, but pressure is there. So yeah, correct. So P. So yeah, RT capital M, the MOV I put it together, right? I bring the volume down, correct? That's what you're doing, right? So yeah, so P, R, T, M. So MOV is actually the density, right? Yeah. So density is what? Yeah, the M times P over RT. Right. Working you get, right? So mass over volume is density, so replace density. The number of mole we can convert to mass over molar mass, right? M over capital M. We got this answer, correct? Okay, until 3 is like a warm-up question. Okay, not a challenging one, just introduction slowly. Question 4 itself can be a little challenging one. Okay, so let me hope some of you can give me the working for the 4. Okay, we go for 4. This is the third one. Okay, hope you got the idea. Okay, so let's we go to the 4. Yeah, 4 like quite a complete ideal gas question. Okay, read the question for 2 minutes for you. Come on. Try to get the answer in the bracket. I hope you have a list of formulas at the side. Already record down. So check which formula is suitable to find these answers. Free electron in a metal move about a continual random motion. So electron is moving around. We know that, like a molecule of an ideal gas. So the kinetic energy of 1 mole of free electron. 1 mole of free electron. The total kinetic energy of 1 mole of free electron is 3 RT over 2. The one we learned earlier is 3 over 2 kT. kT, kinetic energy of one particle. 3 over 2 RT is actually kinetic energy of 1 mole of particle. If you derive. Do you agree? Kinetic energy of one particle is 3 over 2 kT. Okay. The kinetic energy of 1 mole, if 1 mole means the 3 over 2 kT multiplied by the Na, right? Avogadro constant, correct? 3 over 2 kT times Avogadro constant, 1 mole of one particle in 1 mole. So K times Na is what? K times Na is your R, right? So 3 over 2 RT lah. So 3 over 2 RT is the kinetic energy of 1 mole of electron, 1 mole of particle. 3 over 2 kT is kinetic energy of one particle. Okay, it makes sense. So 1 mole of electron has the kinetic energy of 3 over 2 RT. They never asked us to prove, but this is how it should be. Okay. What they want now? The kinetic energy of 1 mole of electron at 20 degrees Celsius. So this, okay, straightforward, right, for typing. So what is the kinetic energy of 1 mole of electron at 20 degrees Celsius? So 3 over 2 RT to be used, right? 3 over 2 RT. T just substitute the temperature, 20 degrees Celsius plus 273.15. Should be the kinetic energy, 3.65 kilojoule. Okay. So if you got the answer for the 4, just 302 RT, the T just 20 degrees Celsius changed to Kelvin. 20 plus 273.15. So you get 3.65 kilojoule or 3,650 kilojoule joule. Okay, try to get the next answer. B. The mean kinetic energy of a free electron at 20 degrees Celsius, then later at 1500 degrees Celsius. So part 1 is easy, right? Mean kinetic energy of free electron at 20 degrees Celsius. You know 1 mole of kinetic energy at 20 degrees Celsius already. So 1 mole of electron, you know the energy is 3.65 kilojoule. So one free electron is 3.65 kilojoule divided by the Avogadro constant, right? So 3.65 kilojoule divided by the Avogadro constant, you get the kinetic energy of one electron, right? Because the 3.65 is for 1 mole, right? 1 mole consists of 6 times 10 power 23 number of particles. So Avogadro constant use how much? 6.02 times 10 to the power of 23, right? Okay, use the Avogadro constant. To get the second answer, 6.06 times 10 power negative 21. Okay, so we get the two answers ready. 3.65 kilojoule and the kinetic energy of 1 electron. Okay, the part 2. What is the kinetic energy of 1 electron if the temperature is at 1500 degrees Celsius? So how do you find kinetic energy of 1 electron at 1500 degrees Celsius? If you don't want to use 3 over 2 RT is fine. You straight away can use 3 over 2 KT, right? Right? I think if you really remember, I think 2 straight away can use 3 over 2 KT. But the question insists you can't use, you must use 3 over 2 RT only. Let's say the question insists you only can use 3 over 2 RT. Then how do you do the kinetic energy of 1 particle of electron? You find kinetic energy of 1 mole at 1500, right? So 3 over 2 RT, T put 1500 degrees Celsius in Kelvin. We get the kinetic energy of 1 mole of electron. Then divide by Avogadro again, the same method as you do for the 2. But the temperature only 1500. So we get that energy, 3.69 times 10 to the negative 20. Okay, so far the PV equals to 1/3 NMC squared. This formula not yet involved, because this is a big what do you call discovery one under kinetic theory. Okay, look at hopefully for the next question. Next question, yes. Hope you get 4, all of you. this I need working. These last two, come on. Yeah, the last two questions. 5. This links to the new formula. PV equals 1/3 NMC squared. Which is used to develop 3O2 kg. So the RMS speed of hydrogen gas at STP is 1840. Calculate the new RMS speed at 100 degrees Celsius. The pressure, the volume kept constant. So the RMS speed of hydrogen is 1840 meter per second at STP, standard temperature pressure. Standard temperature pressure is how much? What is the temperature? 0 degrees Celsius, right? 0 degrees Celsius. Yeah, 0 degrees Celsius, right? Okay, just for a while, just STP values stated on top, right? Yeah. So the STP value is 0 degrees Celsius and 100,000 Pascal. That's your pressure value and temperature value for STP. Can we go back? So STP temperature 0 degrees Celsius, pressure is 100,000. Okay. Okay, now do the 5. So at 0 degrees Celsius, pressure 100,000, the speed of the particle is found to be 1840 meter per second. The RMS speed, root mean square speed. Yeah. Calculate the new RMS speed at 100 degrees Celsius. And the pressure and the volume kept constant. Pressure and the pressure. Oh, yeah. Calculate the RMS speed and the pressure. You need to know the pressure. With the volume kept constant. You should get 2150. How to do this? 2 minutes for you, come on. Come on, think, just 2 minutes. Try to figure out how you can solve this problem. But what hint I like to tell you here is, what hint I would like to tell you here, when you do this question 5 just now, put this in your mind. The mean square speed is proportional to temperature, remember. The mean square speed is proportional to temperature, not root mean square speed. So the question asking for root mean square speed. Question asking for this. This is root mean square. Question asking for root mean square. Remember, mean square speed is proportional to temperature. So when 0 degrees Celsius, the speed is, the RMS speed is 1840. The speed given is RMS. Come on, any mathematical genius here can get the answer. 2150. Try to use this knowledge. Mean square speed is proportional to temperature. I don't want to do first. Just give 2 minutes for you. square speed is proportional to temperature. But if RMS speed is temperature. So you have to convert to deal with temperature. You have to convert the root mean square speed to mean square speed. Okay. You have to get the mean square speed at 100 degrees Celsius. You need to get the mean square speed first. Then only you can get root mean square speed. Okay. Because you have to remember, not root mean square speed is linked to temperature. The mean square speed. Okay. When mean square speed double, when temperature double, mean square speed double. Yeah. So use this proportionality. Root mean square change to mean square first. Then you get the mean square for the 100 degrees Celsius. Then you root it, you get the answer, RMS. Okay, 2 minutes for you, come on. Those who get 2150, good. So what they said, so RMS speed, we get RMS speed, root mean c squared. Okay, okay, this is the first one. Then we have mean square speed, mean square speed. Okay, this is the second one. And third, I want to put the temperature linked. Okay, for the first case, the temperature, standard temperature, 0 degrees Celsius. So it's 0 degrees Celsius, how many Kelvin? 273.15 Kelvin. When the temperature is 273.15 Kelvin, the root mean square speed is found to be how much? 1840. Okay, we don't know the mean square speed. Right. Now the question, the second one, they're asking what? What is the root mean square speed? Asking what is the root mean square speed? And the temperature is how much? 100 degrees Celsius. That means 373.15 Kelvin. And the temperature is 373.15 Kelvin. Okay. Okay. This is the summary, right? 1340 for this temperature. This is the mean square. 373. What is the mean square? Question has been asked. But the one linked to temperature is your mean square speed. Okay. So the RMS speed. Okay. So if you know this mean square speed, you root this value, you get the RMS speed. Right? How to get this mean speed? This proportionality. You know this mean speed, right? You can find this mean speed. Just this root mean square speed, you do what? You square it, right? Right? Okay, can you get some idea? Okay, I think this is in summary. So 1840, what is the mean square speed? 1840 square, correct? Okay. So for the sake of getting the question mark, okay, we need to find this mean square speed first at 373.15. Okay. So what's the proportionality? The mean square speed proportional to the temperature. So first set of reading is what? 1840 squared should be proportional to 273.15 Kelvin, right? This is x. I put this as x. We find the x first. So the x, okay, the x, whatever you got here, the x is proportional to 373.15 Kelvin. Okay. First equation, second, right? Can you find the value of x? So how much the x? You can do 2 divided by 1, right? Second divided by 1. So x over 1840 squared equals to what? 373.15 over 273.15, right? Okay, so we find the x first. So 373.15 over 273.15 times 1840 squared. Okay, whatever answer you got here, what speed is that? Whatever x you got here is what speed is this? Here, mean square speed. X is a mean square speed. Question 1 root mean square speed. Whatever x you got, you just square root. Square root, you got root mean square. This is a very common question in guess again. They will purposely give root mean square speed for this temperature. For different temperature, they will ask root mean square speed. But the playmaker is the mean square speed. You need to get the mean square speed. That's what it proportional to temperature. Yeah. You need to get the mean square speed first, then only you can find root mean. Okay, try to get this idea properly. Okay. So whatever x you got, so now the root mean square speed is equals to root of x, root of x. Whatever x you got, root of x, that's the answer, meter per second. Okay. So do you got the answer? Anyone got the answer? Got a different answer? What's the answer stated? Okay, go. You got 2150. 2150. Okay, good. Okay, so remember, so they give you RMS speed, but to relate temperature, you have to go to mean square speed. Okay, mean square speed is proportional to temperature. It's proven. Okay, so can you continue after that? Can you find the pressure now? What is the pressure of the gas at 100 degrees Celsius? What formula to be used? What is the pressure of the gas at 100 degrees Celsius? Volume kept constant. Oh, that's a big relief. Volume say kept constant. So 2 sets of reading, right? Pressure 1 T1 got T2 they asking. V is the same. T1 you know, T2 you know. So what formula? Yeah, we can go for that. We don't need to go for PV equals NRT, right? Just T1 V1 over T1 equals to P2 V2 over T2. You can go there. 2 sets of reading. Okay. Whenever idle gas, you got 2 sets of reading: P1 P2, P1 V2, T1 T2. So you don't need to go for PV equals N. So those who thought of formula to find pressure P1 V1 over T1 should be equals to P2 V2 over T2. Then correct track. Then you got the idea. So use that formula. Can you find pressure? Let's find the pressure. So pressure, how do you find pressure? Just P1 V1 over T1 equals to P2 V2 over T2. Of course, volume V1 V2 is same lah. So V1 we can cancel. It's actually P1 over T1 equals to P2 over T2. P1 is how much? P1 is standard temperature pressure. So standard temperature is how much? 100,000 Pascal. The atmospheric pressure 100,000 Pascal. P1 is 100,000 Pascal. T1 is 0 degrees Celsius. So T1 is 273.15 Kelvin. P2 we are looking for. T2 is how much? 373.15 Kelvin. Okay. Simple. Okay, then you got the answer. It's locked. It is locked. Okay. Hey guys, so hope you got the 136 kilopascal. Okay, it's your O level knowledge, right? Or SPM knowledge. 136. You can survive without the new idea. Okay, so we're going to stop after the last part. Just the last part. Question 6. We'll do next class. Get the last part. Compare your answer for the speed of oxygen molecule at 100 degrees Celsius. No. Yeah, compare. The speed of the hydrogen compare with the speed of oxygen at 100 degrees Celsius. So in this room got oxygen and hydrogen gas. Okay, which is faster? Oxygen faster or hydrogen faster? Of course, which is faster? Of course, hydrogen going to be faster, right? Because lighter. But what is same for both of them? What is same for both of them in this room? The kinetic energy should be the same, right? Same temperature, same temperature, all particles have the same kinetic energy, right? So, can you find the ratio of the speed? So you start your working with what? What same? Kinetic energy of hydrogen is same as kinetic energy of oxygen. Okay. So from there, you can find the ratio of the speed. Okay. So how do you do? So the kinetic energy of what? Hydrogen should be same as kinetic energy of the oxygen, right? Oxygen, sorry. So half mc squared, okay, should be equals to half mc squared of the oxygen. So they want oxygen, hydrogen over oxygen. So the c squared of hydrogen over the c squared of the oxygen should be same as mass of what? Mass of oxygen over the mass of hydrogen, right? Right, rearranging, right? Makes sense, half cancel. So what do you get? Mass of oxygen is what? 32. So 32 over 2, 16. Yeah. Okay. But they want, this is ratio of mean square speed. This is ratio of mean square speed. They want ratio of the speed. That means average speed. This mean square speed is same as like v squared. It's a v squared. They want the ratio of v. So what do you have to do? So you square root the 16, right? Square root the 16. Actually, the speed, if they just say find the ratio of speed, it's actually same as the speed, the RMS speed. It's RMS speed. Only the RMS speed is equivalent to the average speed, the average speed. So here you get mean square speed ratio. So you square root this, you get the ratio of the root mean square speed. So it's root of 16. So it's 4 times. So hydrogen travels 4 times faster than the oxygen in this particular temperature. Okay. Okay, so I stop here. So 1.55. So question 6, give a try. Okay. Then I will discuss tomorrow for a while. But get the working. Get the working. Okay. Okay, thanks. Stop here.